In this video I'm going to show you how to derive the rate equation for an enzyme substrate reaction. As shown here, we have the reaction flow. So we have on the far left side the reactants, which is of course the enzyme and the substrate. These reversibly can combine into an enzyme substrate complex, and then an irreversible conversion of the substrate to the product often occurs, resulting in the enzyme being regenerated, of course, as it is a catalyst. So let's look at how we derive this into a rate equation. The rate of this reaction is, of course, the rate of change of the product formation, defined as follows, which we can call V, meaning the rate of reaction. This is simply equal to K2 times concentration of ES. So what is the concentration of the enzyme substrate complex? We can find this by taking the steady state approximation, which says that after an initiation period, the rate of change of concentration of a reactive intermediate is equal to 0. Essentially, it is being formed at the same rate in which it is being consumed. We can take this approximation for the enzyme substrate complex and define dEs dt equal to 0. If we then define what the rate of formation of enzyme substrate complex is, i.e. what the dEs over dt is, this is equal to the rate at which it forms, K1 ES, minus the rate at which it falls apart into enzyme and substrate, minus the rate in which it forms product and enzyme. If we rearrange this equation, noting that we have 0 on the left, we can define ES equal to K1 ES over K minus 1 plus K2. This, however, isn't our final expression. You may note that the enzyme substrate complex concentration is intrinsically linked to the enzyme concentration. If we think about it, at the start of a reaction, before any enzyme forms any enzyme substrate complex, we have a concentration which we can call E0, the initial enzyme concentration. E0 is equal to the amount of enzyme and the amount of enzyme substrate complex throughout the entire reaction, as the number of enzyme molecules doesn't change. Therefore, we can define E equal to E0 minus ES. If we plug this back into our equation, we can now define ES in better terms. Can, of course, take the ES over to the other side of the equation. We can then simply add the 1 to the fraction inside the brackets and divide through by the fraction on the left. Now cancelling K1, K minus 1 and K2 on the denominator and the numerator of the two fractions being multiplied, we get a final expression for ES. Remember from the start of the video that the rate is equal to K2 times ES. We now have our rate equation. Note that K1, K2, E0 are all constants, so we can take this as a new constant called K alpha. Similarly, K1 plus K2 is another constant we can call K beta. This is our simplified rate equation. So let's look at a couple limits. Vmax is the maximum rate of reaction, and this is when the concentration of S approaches infinity. In this case, K1S dominates the denominator over K beta, so we result in having K alpha over K1S times S. Cancelling these two concentrations of S, we get a constant K alpha over K1. When the substrate concentration gets so high, it has maxed out all of the enzyme active sites, therefore adding more substrate won't accelerate the reaction. In fact, the reaction is being limited by the concentration of enzyme instead. Note that K alpha is still proportional to the initial concentration of enzyme.